Hello, my name is Mick Petzold. Welcome to this presentation which discusses David Gay and Alex Aiken's paper on memory management with explicit regions. There are two popular memory management techniques. The first is explicit allocation and deallocation. For example, the C language is Malloc free. And since this paper focuses on Malloc-free implementations as representative of this technique, I'll call it that throughout my discussion. Malloc-free is an efficient technique. It is complex and does bring several issues. I'll be explaining these issues in more detail further in, but for now, here they are. These issues include allocation and deallocation. Mismatches are common. Often you get dereferenced dangling pointers, heap fragmentation and boundary issues, how to size, when to allocate, and finally remembering to free memory. The second technique that's common is garbage collection. It is very convenient and safe. However, it's hard to know when to scan, how often to scan. Does it require rearranging? Because of this, it often is running at unpredictable times. This can result in difficulty in predicting performance, such as memory consumption. An alternative approach is region-based memory management that addresses most of the Malloc-free and garbage collection issues. In this scheme, allocated objects are explicitly placed in regions by the program. Memory is freed by destroying a region, freeing all objects within it. Gay and Aiken show that explicit regions are faster than the other two more common types, and on average consume less memory as well. This approach is also great for complex data structures. This C code provides a simple example of region-based memory allocation. A new region is created, R3 in this case. Each iteration of the loop allocates an array and places it in R3. Finally, memory is freed by destroying region R2 by calling delete region. These next few slides provide an example demonstrating the region-based memory management technique. Here we see two regions, R1 and R2. Each region has a collection of explicitly allocated objects. There are 6 in R1 and 8 objects in R2. Because they're explicitly allocated, regions can be set up to hold specific types of objects. For example, R1 could be holding small objects and R2 large objects. Objects often have reference pointers. Note that there's two types of pointers. External pointers that point to other objects in other regions, and internal pointers that point to an object within its region. Here we're creating a new region. Note that this could be done using our example code just discussed. Specifically, the line region R3 is equal to new region. That will do it. Notice that R3 is initially empty. We can add objects at any time to our 3 regions or update any existing objects. For example, by adding or removing regions and normal pointers. Here we are running delete region of R2. Gay calls this an unsafe practice because deleting a region could result in dangling pointers, including dangling pointers that can be dereferenced. This is not a good thing to do. Right. We've just seen that region-based memory management does have several advantages. Those include allocated objects can be placed in an area of memory called a region, explicitly specified by the program. Objects can be placed by type. For example, objects accessed by the app multiple times can be assigned to a single region, which improves data locality. We can easily bulk deallocate all objects within the region by deleting a region in which they belong. However, as we just saw in the prior slide, there's that big problem in that it allows unsafe behavior. A region R can be deleted even if other regions have pointers to objects in R, resulting in dereferenced pointers. Also, freed objects within destroyed regions are deallocated, and there is a possibility of destroying regions more than once if the coding is bad. Gay and Aiken provide a solution to this. By maintaining a reference count of external pointers to the objects within the region, we can then only delete a region and therefore deallocate objects after determining that no references exist. Now we could see that by updating the delete region function to allow deletion of a region only when that region's reference count equals 0, we can prevent dereferenced pointers. So in this case, a call to delete region R2 will result in no action being taken because region R1 has 2 pointers to it, and region R3 has 1 external pointer to it. However, counting references can be difficult to do. We'll talk about that next. For their paper, Gay and Aiken implemented the prototype safe region-based memory management CAT system as an extension of C. This allowed them to compare existing allocation-intensive programs modified to use regions. Their prototype also requires language and compiler support for 2 reasons. The first being the compiler needs to generate the reference counting code, and the second, all live local variables containing pointers must be located. This information is only available in the compiler. Gay and Aiken modified their LCC compiler to handle CAT in the runtime library. By doing this, the requirements on pointers to objects in regions could be ensured during compilation. Now we'll talk about their program extension, their C program extension, CAT. CAT recognizes 2 kinds of pointers, normal pointers and region pointers. Region pointers are the pointers that point to objects in regions like we just saw. In CAT, region pointers are defined with the @ symbol instead of asterisks like normal pointers use. For an example, integer @x. Region pointers are not defined in standard C, hence the need for CAT. Specifically, delete region requires region pointers to count reference pointers. When a region R pointer is updated, 2 reference counts may also require updating because update requires removal of the old existing pointer and addition of the new pointer. Therefore, reference count must be decremented to adjust for removal of region R's old pointer, and it also must be incremented to adjust for the new region R pointer, assuming it's an external region pointer. This means that all region pointers must be initialized. This is the region-based memory management system interface. A new region gets created by calling new region. Objects are allocated with r_alloc, arrays with r_array_alloc. Objects or arrays without region pointers are allocated with r_string_alloc. The memory returned by r_alloc and r_array_alloc, but not r_string_alloc, is cleared. An object's region is returned by region of. And an attempt to delete a region is made by calling delete region X. The deletion succeeds if there are no references to the region in live variables or in other regions, like we previously discussed. This is an example of code that copies a list into a region, does something with it, then later deletes that region. The cleanup list function will be touched on the next slide. I'm not going to get into much detail on this, but it's there if you want to take a look at it. The region library must maintain a mapping from memory addresses to regions for reference counting. The region data structure is shown in the code. A region contains a reference count and two allocators. The first allocator is for normal allocations, r_alloc and r_array_alloc, for region data with pointers. In the second, for pointer-free region data, r_string_alloc. Each allocator maintains a list of 4 kilobyte pages. Allocation occurs on the first page of the list only. If the allocation fits on that page, page 1, then first page plus alloc from is returned and alloc from is incremented. If it doesn't fit, a new page is added until the allocation fits. And if that still doesn't fit, then another new page is added, and so on. Functions r_alloc and r_array_alloc must call the cleanup function to clear the rest of the allocated memory. Functions r_array_alloc must also save the size of the array. The allocators maintain an array that maps page addresses, their memory addresses, to regions. Space overheads are low, 8 bytes per page for the map of pages to regions, and also the list of allocated pages. So the goal of reference counting scheme is to avoid large overhead by referencing counting local variables exactly. An object is allocated and deallocated only once and is therefore inexpensive to do. However, references to an object can change several times, so maintaining exact reference counts can be very expensive. Therefore, Gay and Aiken distinguish between local variable references, which change frequency, from references in the heap, which rarely get updated. So there are 4 components to their scheme. Maintaining approximate reference counts for local variables, pointers to region R from other regions. Maintaining exact reference counts for pointers in the heap. The third one is scanning of the stack to get the exact reference count of local variables when the function delete region is called. And the last component is scanning deleted regions for pointers and objects allocated in R to ensure the reference counts of other regions get adjusted. I'm going to discuss their implementation of their comparison. Memory management with explicit regions performance was compared against 3 Malloc-free implementations and the Bohm-Weiser conservative garbage collector. The 3 Malloc-free implementations are Sun, which is typically the default Malloc-free implementation. BSD, which features fast allocation and deallocation with a very large memory overhead. And Leah, which is Doug Leah's implementation of Malloc-free. And again, the Bohm-Weiser conservative garbage collector. All frees had to be disabled when compiling with this collector to ensure safe memory management. The performance of the safe region-based memory management was compared using 6 allocation-intensive C programs. And they're listed here. CFRAC is a program that factors large integers. Grosvenor transforms a set of polynomials into a Grosvenor basis. Muddle is a bytecode compiler. LCC, as mentioned before, is the modified version of their LCC compiler. Tile automatically partitions a set of text files into subsections based on frequency and grouping of words. And finally, MOS, which is a software plagiarism detection system. So the region-based memory management improvement estimates were determined using 2 criteria, memory usage and performance. Gay and Aiken found that the safe region-based programs used anywhere from 9% less to 19% more memory than the allocator that used the least memory. Performance-wise, they saw speeds from 5% slower to 9% faster than the fastest allocators. Unsafe regions were never slower than other allocators and up to 16% faster than the next fastest. On the MOS program benchmark, by using 2 regions, one for small objects and the other for large objects, they got a 24% performance improvement. And finally, the overhead of safe regions never exceeded 17%. Generally being much lower. Gay and Aiken provided a region-based memory management technique that combined efficiency and safety. Their technique typically used less memory while being as faster than the 2 typical approaches of Malloc-free and garbage collection. A programmer could use this technique to explicitly set the locality of object allocations. This could result in much better performance, as the MOS benchmark showed. Region-based memory management does require C language extensions in a region library. This has not been fully addressed or attempted at the time the paper was written. In my opinion, still a lot more experimentation needs to be done to prove the viability of this approach. Finally, Gay and Aiken do list several memory management works in their paper. The literature on memory management is vast, so I just listed a few works I feel mostly apply to this paper. These are also some techniques that were used quite a bit to implement region-based memory allocation, although all these do it unsafely. Thank you for viewing this presentation, and I hope you gained an understanding of memory management with explicit regions.